Yeah. So welcome everyone to the fifth episode of the third season of the Isogeny Club. Today we are lucky enough to have Peter Kutage giving a talk. He's assistant professor at the University of Birmingham and lead researchers at the Utrecht Lorand University. Yeah, so please, the floor is yours, Peter.
Thank you. So let me share my screen. So hopefully everybody can see my slides. So a quick apology at the beginning. I have a little bit of a sore throat, so that's why I have such a weird voice. And hopefully it will not go away during the talk. So I will be talking about the paper Hidden Stabilizers, the Isogeny to Endomorphism Ring Problem and the Cryptanalysis of pSIDH. Which is a long title, but apt, as you will see at some point. So this is joint work with Ming-Jae Chen, Muhammad Imran, Gabor Ivanyos, Antonin Leroux, and Christophe Petit. And so as this paper will be presented in a couple of days at Asia Crypt by my Ming-Jae, my goal with this talk will be to a little bit motivate the results, motivate the ideas, and there'll be a little bit of an informal talk in the sense that I will not just try to present the actual results, but a little bit how this came about. So the first slide, as I guess is often pretty usual with isogeny-based crypto talks, is a slide about SIDH. Because originally this kind of project started as a different cryptanalysis project on SIDH long ago when SIDH was not actually broken. I mean, pretty much I think everyone has seen the slide, but the main idea was at the time to get some sort of group action on the key space of SIDH, utilizing this torsion point information that is given to you in SIDH. So everything starts with this very simple diagram, which we will be using over and over again. It's a very simple observation, but somewhat useful. So imagine now that you have you draw a key exchange with SIDH, but one of the arrows is actually an endomorphism, right? You can get the key exchange that way, and but it also somehow shows you that that you can actually act on secret isogenies using endomorphisms. So basically, the main observation is that you have an isogeny of a fixed degree from E0 to E, and you take an endomorphism of E0, you can somehow shift that over to a different isogeny of the same degree from E0 to a different curve. Basically, just taking, if the original kernel was generated by A, then the new kernel is generated by theta A. Of course, here you should look at endomorphisms whose degree is coprime to the degree of phi. Otherwise, the degree might change. But if that happens, you get a different isogeny. And then the key observation is this very simple isomorphisms between curves, is that it doesn't matter. This diagram is commutative, so in some sense, it doesn't matter which route you take. So when you factor out E by phi evaluated at the kernel of theta, is the same as factoring out E0 with theta at the kernel of phi. So this is basically a motivation of how you can actually get some sort of group action on the set of fixed degree isogenies. But of course, so one issue is that endomorphisms, they're not really a group. I mean, okay, they are an abelian group additively, but that's not really useful in this setting. So how can you view endomorphisms as a group? So of course, as I mentioned, you should be looking at endomorphisms whose degree is coprime to n. And now it starts to take place. So basically, let the endomorphism ring of E0 be O. and then you can view the endomorphism ring modulo n. And this is a somewhat folklore result that if you take the endomorphism ring modulo n, you just get 2 times 2 matrices over Z over NZ, so over the residue ring modulo n. So this is something that is actually used in KLPT, for example, for prime n, but it's actually true for any n. And it's so the proof can be found in Voigt's book in the supersingular isogeny chapter 42. I mean, obviously it should be chapter 42 because it's the most important chapter of the book. And the proof is pretty simple actually. So it's quite easy to see that you can view endomorphisms as 2 times 2 matrices, but because they act on the n torsion, which is a rank 2 modulo over Z over NZ. But you have to think a little bit more that this action is actually surjective and injective. And basically the thing comes from the fact that endomorphisms, they're a rank 4 lattice. So you basically modulo n, you have n to the 4 choices. And really the choices only matter for every coefficient modulo n. So you really just get n to the 4 distinct matrices, and luckily that's the number of matrices that you have. So this is more or less the proof of this fact. So this is actually true not just for prime n, it's really true for any n. And now what are the ones that are whose degree is coprime? So here the degree really translates to determinant modulo n. So something degree being coprime really just means that it's really an invertible matrix in this ring. So now your group is really just 2 times 2 invertible A matrices modulo n. So how can you again see it as now actually a group pattern? Now it becomes pretty simple, because so now you're looking at cyclic isogenies of a fixed degree. So they can be identified with cyclic subgroups, which are essentially projective points in Z over NZ square. And now the action is just you take a matrix, you take a vector, and you multiply them. And then you get a different vector. And, and this somehow gives you some sort of pretty natural strategy of using this group action. So you have a secret isogeny that you want to find. You create one of the same degree, and then hope that you can find the group element, taking one isogeny that you created to one that is the secret one. So this was somehow the idea from our Eurocrypt paper, which was joint work with Simon Philippe Mertz, Christophe Petit, and Charlotte Weidkemper. And so we tried to attack SIDH, but we really wanted to fit all of this into a hidden shift framework. So the framework that comes up when you try to attack C-side with Cooper-Berg. So we wanted to use this group action in a sense that we want to define 2 functions which are shifts, and then find a hidden shift using a quantum algorithm. So there were many technical obstacles to this idea. First of all, I mean, Cooper-Berg works for abelian hidden shift problems, and real 2Z over NZ is non-abelian. Then, so how do you evaluate this group action? Of course, if you know the secret, then you can evaluate it because it's multiplying a matrix with a vector. But when you don't know it, how do you evaluate it? And so there are 2 before we do that. So since you somehow don't in SIDH, the information is so if you just somehow see the domain and the codomain of the curve, it was better to look at this group action slightly differently, not acting on isogenies, but acting on just n isogenous curves. So just acting on the end curve. So you always see a different end curve when you apply the group action. In some settings, those are the same. If there is like if there is no endomorphism of degree n square, which is non-cyclic, non-scalar, then there is really a one-to-one correspondence between cyclic subgroups of degree n and n isogenous curves, meaning there is no curve when there is like two different n isogenies going to that curve. If that doesn't happen, then you can really view this action just on the end curves and not the isogenies itself. And then the main idea, so I have to go back to this very useful I always will refer to this as the very useful diagram, because then the main idea is that somehow, and this is where the torsion point information came in, is that it's not clear how you can. So basically, what you want is this end curve E prime. And I mean, of course, going this way doesn't really help you, even though you know theta, you don't know the kernel of the isogeny. So this way doesn't help you. What helps you is going the other way. You know the image of phi, and you know how phi acts on a large subgroup. So what you hope for when you want to evaluate this group action is that the kernel of theta, you can evaluate the phi on the kernel of theta. So that will be your strategy in evaluating this group action, is because you know a lot of information about phi, maybe that helps you actually go in this direction and get the end curve E prime. So of course, this whole idea, if you apply it in an SIDH context, only works if the degree when the degree of theta divides the torsion point information B. So obviously, it's easy to see that this is not going to end well. But I mean, there is one thing. So one lucky thing that you can actually do is that theta is not. So when you apply these endomorphisms, you always work modulo n. So when you want to apply a group element, you can choose a representative of that class. So even though if you pick a theta whose kernel, whose degree doesn't divide B, maybe you can pick a different representative of that coset whose degree divides B. So this is a valid approach, but this only works if B is very big. Basically, choosing this this appropriate representative is actually one of the key points in the paper that I'm eventually about to present as well. But in the original version, this only worked when B was very, very big. And even though it looked like an interesting idea, it didn't lead to any improvements. So it was strictly worse in terms of torsion point attacks. So at that time, there were actually better attacks already than that paper, even though this was a completely novel approach. And there were many other technical details. So I just only mentioned to you how I can evaluate the group action. But then, as I mentioned, you have to work with abelian groups. Otherwise, Cooperberg will fail. So you have to restrict your group action. So you have to forget all of the lot of the information that you have, and just restrict to a certain subgroup. And then there were a million other small technical details which had to be dealt with, which made some of the results not so elegant. But if you deal with that, I mean, basically you can really translate it into a hidden shift problem just by looking at this group action, and this is like a transportation problem. So it's really like seaside that you have. You basically pick another isogeny that you like, and then you want to find an appropriate group element that takes one to the other, and it really nicely fits into the Cooperberg frame. So this is where it was at. I think it was a nice result and a nice method, but it didn't give any groundbreaking results at that time. And one of the main issues which I was contemplating with is we were really focusing on putting everything in this Cooperberg framework, because we were not quantum algorithm people. There are 5 quantum algorithms we know. Cooperberg was one of them. So let's try to push for that thing, because that's what we really know. So one natural question is, what happens if you don't throw away all that kind of information? So then the Cooper-Berg framework will not be, because you have a big abelian group. What kind of thing you should try do you think you should try to aim for? And one of the natural ideas is, instead of working with a hidden shift problem, you want to work with a hidden subgroup problem. So if you read the description of the hidden subgroup problem, if I don't have it on my slide, which is probably a mistake, but I can just describe it with words. The hidden subgroup problem is that you have a function from a group to whatever a set, and your function is constant along the cosets of a hidden subgroup. And your problem is to find this hidden subgroup. This looks like a little bit strange explanation of a problem. But then if you think a little bit more, there are basically two cases that you always use this problem. One case is when you have a group homomorphism. If you have a group homomorphism and you want to compute the kernel of this group homomorphism, right? Because then it's true that the group homomorphism is constant along the cosets of the kernel. And the second usual application for hidden subgroup problems is when you have a group action and you want to compute the stabilizer of an element. A stabilizer of an element means all the group elements that fix that particular element. And then these are the two cases. I think basically you can reduce to, maybe it's always you can reduce to the stabilizer case in any case. So when you think of that, then I think it becomes a much more natural problem, because computing stabilizers for group actions is something very, very natural. Why we never hear of it as isogenies is because we're used to pSIDH, which is a regular group action, meaning every stabilizer is trivial, so there's no stabilizer computation. So then, okay, so hidden subgroup problems, they're good for finding stabilizers. Why on earth do I care about the stabilizer? So I will give you like a more formal treatment later on, why you can immediately recover what you want in our context from a stabilizer. But first I will try to give you like an intuition, which led us to look at stabilizers. So modulo some technical details, basically what does a stabilizer of an isogeny mean? It means you have, let's say your isogeny has a kernel generated by A. So then you look at all the endomorphisms for which theta A is lambda times A. So which means that all the endomorphisms for which A is an eigenvector. So you can view endomorphisms as 2 times 2 matrices, modulo n, and then you can view points as vectors, two-dimensional vectors modulo n. And then really it just means you're looking for a collection of matrices for which your particular kernel is an eigenvector. And then, so let's say someone computes this stabilizer. So then you have a bunch of matrices, if the stabilizer is big enough. You have lots of matrices with a common eigenvector. And that's not so hard to compute in general. If you've ever seen the Kipnis-Shamir attack on oil and vinegar without the U, this is basically what happens there. Not quite, because you have a larger dimensional space, but basically very similar, that you have a common invariant subspace of a bunch of matrices, and that's something you can compute. So that's why somehow it makes a lot of sense of going for stabilizers, because then you just somehow look at the common invariant subspace of these matrices, and that will reveal your secret kernel. So this was somehow a little bit of a motivation, and I wanted to extend these results, and then but then the SIDH attacks happened, so it seemed everything is irrelevant and nothing might not be an interesting idea anymore. But then we decided to target a different scheme, with these kind of methods, which is pSIDH. So I'm not going to explain all the details of pSIDH because I think it's better if you just keep it at a high level. So basically, if you view SIDH as, okay, so SIDH is broken, but how can you repair SIDH? One version is the usual countermeasures by Petit, Moria, and Fuozza, that you just give away torsion points up to a scalar. And the other type of countermeasure was, so one other suggestion was pSIDH, which said try to use isogenies with big prime degrees. Because, I mean, the SIDH attacks, they implicitly assume that you're working with smooth degree isogenies. And this prompted a definition which I think is very, very interesting, and actually found applications elsewhere. For example, in SkiSign HD, basically, is the notion of an isogeny representation. So when do I say I know an isogeny? So of course, when the isogeny is smooth, right, I can write it down. I can write it down as a composition of low degree isogenies, and there it is. But what happens if the isogeny has a big prime degree, so there's no way of me writing it down as a rational map? So then it means that it's some way of evaluating your isogeny at any point. Technically up to a scalar, but for simplicity, let's assume that I can evaluate it at any point exactly. So that's somehow a way of actually using an isogeny, because you can evaluate it wherever you want. And then basically the idea of pSIDH was that you use big prime degree isogenies and you reveal isogeny representations of your isogenies, and that allows you to actually do an SIDH like key exchange and avoid the SIDH attacks because your isogenies have big prime degrees. But in this construction, you reveal basically an infinite amount of torsion point information. You can really evaluate it anywhere. Of course, the cost of the evaluation being the representation of the point. So of course, you cannot evaluate it at a point with which is defined over an exponentially large extension field, because you cannot even write down the point. So the cost of the evaluation is really the representation of the point, but you can really evaluate it anywhere. And this construction really needs like a starting curve where you know the endomorphism ring, because basically your representation is you reveal some endomorphisms on the public curve to make sure that you can evaluate your isogeny. This is called the suborder representation. So these are what help you evaluate your isogeny at any point. So also Antonin came up with the scheme, formalized the hard problem behind this scheme. Is basically, so given the endomorphism ring of E0 and an isogeny representation of an isogeny of degree n from E0 to E1, compute the endomorphism ring of E1. So from a cryptanalysis perspective, this is the most natural problem that you can go for, right? I mean, you cannot write down this isogeny. You can evaluate it anywhere. So what is the kind of information that you want to retrieve in this setting? Is really the endomorphism ring of the polygon. So this is the problem that we actually want to study in this talk. And you can also go look at this from a different angle. So of course, when n is smooth, this problem is easy, and is the isogeny to ideal translation of SkiSign, for example, because then you can really retrospectively every step you just translate your endomorphism rings through the isogeny. But here the difficulty really comes at the setting where n is a big prime. Sorry, I might want to move this one. So our goal is really to apply this so is to look at to apply this group action that was defined before, and now use it to try to attack pSIDH. So the first issue that appears is how do you evaluate this group action? Again, you don't know the kernel. The kernel is defined over a huge extension field. What do you do in this setting? And if you just blindly want to go back to the Eurocrypt 21 approach, you still need this correspondence between n-isogenies and n-isogenous curves, so that there are really no two collisions. But you can be a little bit more clever about this. So when you evaluate this group action, you again go back to this useful diagram. You again, instead of going this route, you go this route. But now the trick is that when you're going in this route, you can actually transmit the isogeny representation going that way. So then what you can say is you're acting on isogeny representations now. Right? So now your group, when you view the group action, you're given two curves, you're given an isogeny representation, and what the group action does, it really compute the group action and then compute the corresponding codomain curve and the new isogeny representation corresponding to that isogeny. And luckily, this is pretty handy because isogeny representations and isogenies, they are in one-to-one correspondence now. So that's actually proven in Antonan's paper. It's also not so hard to prove, right? I mean, if you have two isogenies which have the same, have the same isogeny representation, then from going one-to-one curve to the other curve, then if you subtract them, you get an isogeny representation which is zero everywhere. So if you take it big enough, it has to be the zero isogeny. Okay, so now one novel idea that is useful and is pretty useful in the pSIDH setting is what you will be going for when you are, because I didn't really quite mention how you evaluate the group action. There is one small catch actually, but whenever you compute this group action, the way to handle this technical issue that still appeared in the EC21 paper is that you're now acting on isogeny representations. And that's pretty good because they're in one-to-one correspondence with cyclic subgroups. You're really mimicking the real group action. Yeah, so I took a quote from the Harry Potter book, which I slightly rephrased. It is our stabilizers, Harry, that show that what we truly are. This is really, I mean, the next line, if I put that word, then it comes out of context. But it's really the thing that the idea of this approach is really somehow not focusing on the one isogeny that you want to find. You really focus on this whole collection of the isogenies, and then what really somehow tells you what is happening is again really the stabilizers. So what are these stabilizers actually? So it's not so hard to calculate what they are abstractly, because you have a very simple group action. You act with matrices on vectors, right? So, and the stabilizer is really just something that for which the vector is an eigenvector. So what is the stabilizer of 1, 0? So that's not so hard to compute. If you just write it down as A, B, C, D, and then you multiply, you get A and C, right? If you multiply A, B, C, D with 1, 0, you get A and C, and this will stabilize the group 1, 0 if C is 0. So hooray, the stabilizer of 1, 0 is really upper triangular matrices, and then it's not so hard to see that if you want a stabilizer of a different element, it's just going to be a conjugate of that. And so what is proven by this very simple argument is that every stabilizer is just a conjugate of the upper triangular matrices. And this is what is called, in the literature, this is called the Borel subgroup. Weirdly, this appeared in the isogeny-based crypto context when in the context of level structures as well. But I mean, yeah, so this is what it's called. So these are called Borel subgroups. And as I mentioned, yeah, so this is computing stabilizers is always a hidden subgroup problem. But GL2 Z over NZ is not an abelian group. And then if you, yeah, I wanted to have something funnier here, but I mean, yeah, the quote is the non-abelian hidden subgroup problems cannot be solved in polynomial time. So this is the quote by every cryptographer. And this is not so far away from the truth, but it's not true. So this is something you should take into account. And I mean, I'm not going to survey all the results, but some of the results I want to showcase that it's not quite true. So one thing that I mean, I think is probably the most useful in general is that even if the group, the big group is non-abelian, if the hidden subgroup is a normal subgroup, then there is a polynomial time algorithm to find it. I think this is a result by Hallgren. And I mean, this is pretty important because if you take a homomorphism, then the kernel is always a normal subgroup. So computing kernels of homomorphisms, even for non-abelian groups, is polynomial time. Unfortunately, for stabilizers, this is not true. So Borel subgroups are not normal subgroups. I mean, upper triangular and lower triangular, those are conjugates, but not the same. So this will not help us. Okay, so another exception, if the group is not abelian, but as close to abelian as it gets, which are nilpotent groups with nilpotency class 2. So nilpotent groups are, I mean, there are many definitions. I guess one definition is this, the direct product of prime power groups. Sorry, so of p groups. So they're the direct product of their Silov subgroups. But there is also these definitions through these central series and commutators. And then basically nilpotent groups of nilpotency class 1, those are the abelian groups, and class 2 is something that is as close to abelian as it gets. Again, not our case. Luckily, I mean, there are probably other examples. So there is a survey paper by Charles and Van Dam called Quantum Algorithms for Algebraic Problems. It's a little bit outdated because it's from 2010, but I mean, it hasn't changed that much since then. So it's mostly sporadic results, but I mean, people should be aware of those results as they might pop up in some cases. And one of the the cases that luckily is exactly our case is the case where the big group is GL2 over or FP, or I mean, in general, the first result was GL2 FP, and the hidden subgroup is a Borel subgroup. Basically, the reason somehow that this is a special case is that it's a group action where the stabilizers are very, very big. Basically as big as they get. So somehow the hidden subgroup is very, very big. So this is what can be somehow leveraged. And then basically the reduction goes, it reduces to something called the generalized hidden shift problem, which I think on its own is also quite interesting for a cryptography context. So probably everyone has heard of the hidden shift problem, that you have two functions from an abelian group to a set, and those are hidden. Those are shifts of each other if fx is gx plus h. And a generalization is when you have many functions, and each of them is a shift of the previous one with the same h. And basically, if you have many of these, basically almost for every group element, or like one over polynomial many fractures or something, so it's for almost all group elements, then you can solve this in quantum polynomial time. Yes. So one thing, so in our paper, if n is prime, we can just basically invoke a result by, I think, Ivanyo, Shanta, and Prakash, I think. But we also generalize the result for arbitrary n. So not just for prime n, but for arbitrary n for the quantum algorithm. But what is kind of funny is that you can, if n is smooth, this problem can actually be solved in classical polynomial time. So just to reiterate what the problem is, so you have a group action of GL to Zn acting on Zn square, and you want to and there is an element S in Zn square, and you want to compute its stabilizer. And when n is prime, this was already known. For arbitrary n, you can generalize the quantum algorithm. But what is somehow strange is if n is smooth, say a power of a prime, small prime, then you can actually find this stabilizer in classical polynomial time. And the idea is basically as follows. So, so for notation, I will use V as Zn square. And I will suppose that n is a power of L, but as a small prime, you can generalize for arbitrary smooth one using a CRT approach. And mainly the idea is that you take this S, or I mean, you can take the subgroup generated by S, and then you try to find its intersection with L to the I times V recursively. So basically, you somehow look at S modulo L square, modulo L cube, and so on. And then, of course, if you do, and you do this somehow iteratively. And the key lemma is a very simple lemma, is that you can actually use for testing whether an element is in H or not. And that lemma is that if you have an element sigma, and sigma plus sigma plus 1 is also in the group, so it's invertible modulo n, then it is in H if and only if f, which is the hiding function, so it's just a natural function that you associate to this group action by fixing an element S and then mapping G to G star S. So if f sigma plus 1 is the same as f1. And then the idea somehow is, I mean, it's easy to see the first step is that you take so when you want to compute the intersection with L to the k minus 1v, you can somehow do it by brute force by looking at, there will be L plus 1 possibilities. Basically, you can really view this as in terms of like isogenies actually as well. So there are L plus 1 possibilities, and you can test using this very simple lemma whether the thing is in, which one is in H. And then when you find it, you iterate this kind of approach. Yeah, so this is the most detail I'm going to get about this approach. So the more details are in our section 3 in our paper, but this is a result that is interesting on its own, I believe. That when n is actually smooth, you don't even need to resort to pot. So one other small thing that we need to solve is so I mentioned that I'm working with the endomorphism ring modulo n, which is isomorphic to 2 times 2 matrices. But I actually have to work with matrices in these approaches. So I cannot just work with the endomorphism ring modulo n. I really have to work with them with as 2 times 2 matrices. So I have to compute an explicit isomorphism between these two things. And then usually what you would do, right, is I have an endomorphism, I evaluate it on the n torsion and do some discrete log things, and then I get a 2 times 2 matrix. So that will fail for multiple reasons, mainly because the n torsion is defined over a huge extension field, so I cannot evaluate my endomorphisms on a huge extension field. One point is defined over a huge extension fields. So instead, I somehow use the internal structure of this ring and trying to find an explicit isomorphism between O over NO and M2 Z over NZ. In general, so this is a very, very, very special case of a much more general problem, that when you're given an algebra A isomorphic to M and K, given by some multiplication table, meaning you can really do computations in the algebra, then find an actual explicit isomorphism. This problem is actually pretty interesting on its own. Not for finite fields, but for when K is a number field or a function field of a curve. It really relates to some really interesting problems, relates to norm equations, parametrizations of algebraic varieties, finding generators of elliptic curve, so the Mordell-Weil group, and some more. But I mean, this is a very special and easy case of this very, very general problem. And this is a problem that actually is implicit in KLPT as well. So if you look at the KLPT algorithm, they also work purely with 2 times 2 matrices. And I mean, they just write 2 or 3 lines regarding how they do this explicit isomorphism. I mean, it's not very hard. Basically, the idea is that you find a zero divisor in O over NO. And then if you have a zero divisor, that gives you a minimal left ideal. And then you can look at the action of the algebra on this minimal left ideal, and that will give you an explicit isomorphism. And how do you find a zero divisor? It just means you want to find an endomorphism whose degree is divisible by n. And then if you write down the norm equation of your maximal order and then solve that modulo n, so that's solving a quadratic form modulo n, and that is pretty easy. So that's how it works for prime n. For completeness, we wanted to solve this actually for non-prime n in the paper as well. Non-prime n is more like a technical addition. So again, you can somehow CRT this. So you only have to care about prime power n's, and then prime power n works in a fun fashion algebraically, if you like, very like abstract algebra. So basically, you find an element which is an idempotent. So let's say you're working with L to the K, and then you find an idempotent modulo L. So it means that when you look at the radical of your algebra, it will be M2FL or whatever. So you invoke your original prime finding algorithm, prime version algorithm, that gives you an element which is an idempotent modulo L, and then you start lifting it modulo L squared, modulo L cubed, modulo L to the K, and then it'll give you an actual idempotent, and that will again give you a minimal left ideal as before. Yeah, so this problem can also be handled. So now, if you put all of this together, what do we have? So now we can represent O over NO as 2 times 2 matrices. And suppose now we can actually compute the group action. Then we can utilize the quantum machinery to compute the stabilizer. So why did I say that the stabilizer is really the thing that matters, besides this eigenvector argument, which was more of a motivation? So for that, we have to understand what these stabilizers really are. So do they have, and they weirdly, they have a very special meaning, and which I think is important because it's useful in other contexts as well. So let phi be the secret isogeny. So let's we want to look at the stabilizer of this phi. So let I phi be the corresponding left ideal of the endomorphism ring of E0. So if I take an element from an endomorphism from this ideal, it means that it vanishes on the kernel of phi. Right? This is the definition. So automatically everything in I phi will be a stabilizer because they will take everything to not quite, sorry, that's not quite true actually. But anyway, so what is definitely true is that if you take an element theta in I phi and then evaluate it at the kernel of phi, you get 0 because that's the definition of I phi. So now that tells you that if you take a scalar matrix, that also will stabilize obviously the secret subgroup. And then so this implies basically that if you take Z plus I phi, those will be in the stabilizer. Here I really mean you basically because I'm looking at group actions, so you have to look at all the invertible elements in Z plus I phi. But it's not a big deal for our case. So okay, so all the elements of the form Z plus I phi will stabilize the kernel of phi. But what can we say? Is this everything? And it is indeed everything, because take an element that stabilizes the kernel of phi. So it means you take let the kernel of phi be A, or generated by A. So that means that sigma A is lambda times A. And that means that if you take the endomorphism sigma minus lambda, that's in I phi. Which is exactly means that sigma is in Z plus I phi. And what is this Z plus I phi? So again, if you look at what is written in ski sign, this is exactly something that is called an Eichler order. Why? Because you take the endomorphism ring of your domain curve, you take the endomorphism ring of the codomain curve in a way that and then you intersect those. So it will be intersection of the two maximal orders corresponding to the appropriate of this left eye. Okay, so the stabilizer just became more interesting because it really has a very nice meaning in terms of isogenies. It is really the Eichler order corresponding to the secret isogeny. So, so this is called an Eichler order of level n, where n is the degree of the isogeny. And then, okay, so this is what I got with this stabilizer approach. Well, how do I get? So what I need. Sorry, there's a typo. What I need is the endomorphism ring of the codomain. So how do I get that from this Eichler order thing? This Z plus I phi. There's two ways, and I will try to explain the first one in more detail. It's a little bit vague what is written here. So so basically what I want is the I phi part, right? So I have Z plus I phi, but I want the I phi. Once I have the connecting ideal, I have the endomorphism ring because I just compute the right order of that. Because I know everything I know the endomorphism of the starting curve. So how do I get rid of this Z? And this is something that might not be well written in our paper, and also never really nice written in ski sign. It's again a little bit folklore, so I think it's useful if I try to explain it a little bit further here. So say you get a matrix which is somehow an integer plus an element in I phi. So how do I get the I phi part out of this matrix? So if you look at this last line, the I phi part is really the lambda for the sigma A equals lambda A. So what I do is I look at my matrix, compute the eigenvalues of the matrix, because if I subtract the eigenvalue, I will get an element which is non-invertible. And this is basically what I want. So I want the non-invertible part. So when n is prime, there are usually two eigenvalues. One of them will be, I guess one of them will be the correct one. I don't think both of them will be correct, but I mean, you compute the eigenvalue, subtract that, take that, and then that will most likely generate your ideal already, and then compute and then check whether that is correct. If not, then you choose the other one. The other approach, so this is the linear algebra approach, that you somehow look at matrices and their eigenvalues. The other approach is, I guess, is more the natural kind of approach that you would do, is again going back to this EC21 idea a little bit. So, okay, I have a secret isogeny. I computed its stabilizer. Now I choose a different isogeny, but this time I was the one doing the choosing. So I know the stabilizer already. I have two stabilizers. So those stabilizers will be conjugate, because each of them are conjugate to upper triangular matrices. And that's not so hard to actually compute an explicit conjugation between the two. And once I find an explicit conjugation, basically, I already found an element that takes one kernel to the other one. Again, basically, in the end, you have to go through this useful diagram, which, so there are some things which I overlook at this point. But basically, again, the idea will be that basically finding a conjugating element between stabilizers is really finding the transporting element. And this is explained in this last remark, so that this is nothing very hardcore. Basically, if you have two elements, x and y, and G takes x to y, then it's easy to see that the stabilizer of y is just G stabilizer of x and G inverse. I mean, basically, if you do that, so if you take an element in the stabilizer of x, let's call that h. So what happens if I take GH, G inverse y? So GH, G inverse G star x, then the G's will fall out. The H will fix the x, so I get G star x in the end. So this is a very elementary argument. And this is, and the reverse is also not so hard to see. So whenever I find the conjugating element between stabilizers, that just gives me a transforming element from one to the other. Okay. So how do I evaluate? So now basically what is missing is how do I actually evaluate this group action? So I put this very useful diagram here at the end as well. And again, as I mentioned, I do this trick that I don't go this route, which I'm supposed to go. I go phi, and then I go here, and then voila, I'm in a very nice situation because I can evaluate phi anywhere I want. So I evaluate it on the kernel of theta, and then I can compute this isogeny, and through this isogeny, I push through my isogeny representation. One teeny tiny obstacle here is, as I mentioned, okay, you can evaluate your phi anywhere you want, but the thing has to be defined over a small extension field. Otherwise, you cannot even write it down. And if I just pick some random theta, why on earth would that be defined over a small extension field? Again, you have this very similar good news, bad news as with the Eurocrypt paper, is the theta is only specified modulo n. So you can try to choose a theta whose norm is power smooth. If you do that, then this approach works, because power smooth norm isogenies can be represented over a polynomially large extension field, and then you can really carry out this thing. But then the issue is, how hard is this problem? How hard is it to find the representative in a given coset that has a power smooth norm? So this is what we call the PQLP problem. Given theta and n, find tau, such a norm of theta plus n times tau is power smooth. So again, if you know KLPT well enough, this is a problem that appears in the KLPT paper as well. But they only solve it for very specific kind of elements. They only solve it for elements which are of the form J times Zi. So this is actually something that is inherent in KLPT. That's why every other step is completely fine in KLPT. But this is the step why they need in the original KLPT that the one of the curves is special. Let's say J1728. Every other step, you don't need that. So why do they do that? Because, and we also do, in the Eurocrypt paper, we solved this for Zi. And the reason they do it because the norm equation gets ugly. So I will quickly demonstrate. This problem is just a simple Diophantine equation. But one lesson with Diophantine equations is that it's really like meeting a lion. So I mean, it's better if you are the one creating the Diophantine equation than encountering one in the wild. So it's much nicer to encounter a lion in a zoo than actually meeting one in the wild. So whenever you meet one in the wild, yeah, maybe you can solve it, maybe you can't. I mean, it's most likely that you can't. It's much better if you explicitly not solve the norm equation that comes in front of you. You just create the one that you can solve, and then you can write hundreds of papers. So, and I mean, I will quickly demonstrate why this is the case. So, I mean, let's assume for simplicity that you really just want to lift an element in J1728. So it means you have an element of the form A plus B times I plus C times J plus D times K. And then, oh yeah, this is obviously a typo here. So then I should have, so the first one. So basically then you're searching for X, Y, Z, and U such that A plus NX, this all kinds of typos here. So A plus NX square plus B plus NY square, and then the rest are correct, plus P times C plus NZ square plus P times D plus NU square. That has to be power smooth. And I mean, it looks horrible. It looks very, very ugly. I mean, but of course, if you take A and B to be 0 and X and Y to be 0, it's a lot less uglier, a lot less J times, so it becomes a lot less ugly. Yeah, I'm kind of curious why that isn't actually divisible by P then. Anyway, so I mean, in any case, if you if you set a bunch of variables to 0, it's much nicer to deal with. But you have 4 variables, it's not homogeneous. It's a super ugly Diophantine equation. So if you want to do it by brute force, which I tried, he's not going to be your friend. Luckily, there is a little bit of hope. So this lifting procedure by taking a different element is somehow multiplicative. So if you can lift an element Z1 and Z2 to being power smooth, then you can lift them separately and take their product, and that still will be power smooth. So one idea could be that, okay, I can lift these J times Zi. Maybe they generate GL2Zn. So maybe it's actually enough to lift these things, and then I just take a couple products, and then I get everything. Unfortunately, this is not going to be the case. So once you take the product of 2 of these elements, you end up in Zi. So basically, the only thing that you can lift is Zi and Zj, and then it's quite easy to see that this will not cover everything, because it will be somewhat quite ugly and so on. And they will not cover every element, and you really need to be able to lift everything. And then the key idea of the paper is that there is one kind of endomorphisms which we overlooked that are super easy to lift. Those are the power smooth ones, because they are already power smooth. You don't need to lift them at all. And then if you use this super teeny tiny idea, you can get a lot further, because so now what you want is you have you fix a power smooth endomorphism gamma, and then you lift a sigma endomorphism. So suppose we want to stay in J1728 for simplicity, but it's easily adjustable to everything else. And then you want to write it as this long product. So you want gamma I to be in J times Zi, but you put this fixed gamma in there. So this is gamma 1, gamma 2, gamma 3 is something that you can lift. Because this was the sorry, there's something appeared on my Zoom, but anyway. So those are something that you can already lift. And then you put these gammas in the middle to kill this weird behavior of taking the product of two elements in J times Zi. And then the lifting part is pretty clear. You lift gamma 1, gamma 2, gamma 3 separately. The gammas don't need any lifting. And then you have 5 elements which are power smooth, so their product is also power smooth. Of course, this is something you have to take into account, though, right? Because if you take like a log n number of power smooth numbers, it will not be power smooth. But if you take a constant number of them, that's fine. So why do you hope that this will work? So the reason this will work is somehow mainly a counting argument, that you lift, because you actually don't need to lift exactly. It's fine if you lift up to a scalar, and then basically you have like n cube different things to choose from, and then what you hope for here is that you have the same number of things on the right-hand side that can occur on the left-hand side. Of course, this is not an argument, because it's just why you would think this kind of approach would work. So that's why you have 3 here and not like 2 or whatever, because this is the number of, this is what you expect. You could actually have a gamma 4, gamma 5 in there as well if you'd like. But this is heuristically should be enough. But how do you compute this decomposition? So you just write up what this actually is, and then you write and you write and you write, and it's quite convenient to use this notation that you write R as Zi, and then you end up with this equation system. So NC is just a norm of C, and these are modular inverses. And then you have this type of equation, and you want to solve for x1, x2, and x3, which are also in R. And basically you can just worry about the less. So what we prove is that basically this will have a solution if and only if this quantity and this quantity have the same norm. If you look at what happens on the right-hand side, the right-hand sides always have whatever x1 and x2 are, they always have the same norm. And basically you can just set them to anything, set this to whatever A and B, unless A and B have the same norm. So basically you just want to ensure, you want to find the x3 such that this and that have the same norm. And that is something that is quite easily, you can easily handle, because basically, so the proof actually uses an adaptation of Hilbert's theorem 90, and it really comes down to the fact that if you have a norm 1 element, it can always be written as x over x conjugate. So this is the original theorem is for I guess number fields. If you have a number fields of or any kind of field with a cyclic Galois extension, and you have an element of norm 1 on top, then that always can be written as like x over x conjugate. In our case, it's a little bit more subtle, because you have not fields, but whatever étale extensions or whatever. I mean, you can really do this calculation explicitly. But if you want to be really, really fancy, you can use Galois cohomology here, which I always wanted to use in a paper. But in any case, if you just write down this these two things, and you want to ensure that these have the same norm, that leads you to a quadratic equation. And the quadratic equation usually has a solution if you are working modulo n, and n is a prime. Usually either like has a 50% chance of having a solution. So when you have a solution, hooray, you've done the lifting. And what happens if you don't have a solution? So then you have to rerun this thing a little bit. So you have to choose a different gamma, basically. Then you choose a different gamma, and what you hope for is that you have to do this a couple of times. One of the choices will be good. And we have a script for it, so it really does work this way. So what is a little bit annoying with this approach is that weirdly, it fails exactly when it's already obvious. So it fails when n has a lot of prime factors, because then a quadratic form is much less likely to have a solution, because it has to have a solution modulo every prime factor of n. So it's exponentially small that it has a solution. We have some approaches to handle this in the appendix. I don't think everyone got that far in our paper to read the appendices, but if you if you are interested in how to try to adjust this to general n, so we need this assumption that, I mean, mainly what we care about is prime n, because that's what pSIDH was designed for, but we wanted something for general n, and it only works if n has at most log n prime factors or something like that. So it fails when it's like has many prime factors. There is, so of course then normal methods just kill the thing, but there is a little bit of a middle ground that is still somewhat unexplored, but there are some things in the paper. So when you put all of this together, all of these small components, you really get the break of pSIDH basically. So evaluating the group action requires this quaternion lifting thing. If you can evaluate the group action, you can compute stabilizers, and from the stabilizers, you can compute the endomorphism ring that you want to. And this gives you a quantum polynomial time attack on pSIDH. So you could, what is natural here is what is there to do. So what are the open problems that pop up naturally in this setting? So one is that this is somehow a completely orthogonal approach to the SIDH attacks. So it somehow works better when the degree is prime, doesn't work when the degree is super smooth, and basically what you have to aim for is being able to evaluate this group action. So it's and it's also kind of agnostic to images exactly or images up to a scalar. So it's a natural idea whether you can combine this approach with the higher dimensional methods. Of course, the higher dimensional methods would be useful to try to evaluate this group action, and then it could be used to break pSIDH, for example. So in that setting, you might, because you don't have isogeny representations in that setting, so in that setting, it might be worth revisiting that approach of just working on using the action just on the codomains, which only works if there is like a one-to-one correspondence between isogenies and or almost one-to-one correspondence between an isogenies and cyclic subgroups of order n. But that's for pSIDH, it's usually not an issue because the isogenies are short. And then the other natural question that I think pops up is whether this new lifting algorithm can be improved to use KLPT. So one thing about this lifting algorithm basically is that you can just purely run KLPT now between two, or any two, or between two maximal orders without going through KLPT, and it's a different approach than what is done in SkiSign. Probably it's worse, so it probably will give you a longer path. But maybe you can improve on this idea or whatever. So I maybe this just purely looking at this PQLP problem resolution that might have applications for SkiSign or something related. Okay, so thank you for listening, and I'm happy to answer any questions. Should I look at the chat?
Thank you very much, Peter. Yeah, so
Oh no, yeah, no, it's just okay, yeah.
Yeah, but if people have any questions, you can just unmute or write in the chat as you prefer. Yeah, thank you very much for a great talk. I actually had like one question that I thought of at some point. So it's very specific to something you said at some point, but did you say that like your this basically I might have misunderstood, but at some point you said something like when the isogeny, when you have like a really long smooth isogeny,
Yes.
or a representation of that, you can use this this hidden shift approach to compute the corresponding ideal, which like in classical polynomial time.
Oh, you mean when the when it's you don't need the hidden shifter. So I mean when you
No,
translate
so
the endomorphism ring or
yeah, so as you said, you can already do this, but
yeah, but
it's
without so you so maybe it has to be power smooth.
yeah, or
Something
I think well, yeah, it's a
So
bit. I
what
just
I
wonder,
was trying to
maybe
say is that basically what you do, right, is you take you have your first endomorphism ring, you evaluate whatever a short degree isogeny, and then that's something you can write down, and then you just I guess compute the corresponding left ideal, and then translate the endomorphism ring by computing the right order. I mean, it's
yeah, you can do that. I think I maybe misunderstood them.
yeah, I think you can do it with yeah. So I mean, it's I don't know which is the best way of actually doing it in practice. I mean, if you
Yeah,
care about
because I
polynomial
thought
time only, then you can. But it's probably stupid to every single time go through. You take a step, you compute the maximum order, and then you compute the corresponding elliptic curve or whatever. Probably, but no, anyway, yeah, no. So it's no, that's fine. No, you actually, yeah. So you every single step you compute the corresponding left ideal and take the right order. And when the isogeny degree is small, then you can compute. I mean, this is just, I guess, it's just the isogeny to ideal algorithm from SkiSign or from GPS.
yeah. All right, thanks. See, are there any more questions? Can give people a few minutes, or we can also officially end the meeting. But remember that it's allowed to hang around a bit more if you want to chat, or if you want to ask some questions you don't want to appear on the recording. But yeah, thank you again, Peter, for a great talk.